high-level architecture of Lucene core, Lucene 4.0 in Lucene. Here you can see high-level architecture of Lucene core here in Lucene 4.0. The Lucene's architecture and implementation has evolved and improved significantly over its lifetime, with much of the work focused around usability and performance, with the work often falling into the areas of memory efficiencies and the removal of synchronizations. Here we will detail some of the commonly used foundation classes of Lucene, and then look at indexing and searching are built on top of this. To get started, this figure illustrates the high-level architecture of Lucene core. With regarding text analysis, chain produces stream of tokens from the input data in the field. Tokens are in the analysis chain are represented as a collection of attributes. In addition to the expected main term, attributes that contains the tokens are the token attribute that contain the token value. There can be many other attributes associated with the token, such as token position, starting and ending of offsets, token type, arbitrary payload data, a byte array to be stored. In the index at current position, integer flags and other custom application defined attributes. For example, part of speech tags. Analysis chains consist of character filters useful for stripping diacritics, for instance, tokenizers, which are the sources of token stream, and series of token filters that modify the original token stream. Custom token attributes can be used for passing bits of per token information between elements in the chain. Lucene includes a total of 5 character filtering implementation, 18 tokenization strategies, and 97 token filtering implementation, and over 32 different languages. This token stream performing specific functions such as tokenization by patterns, rules, and dictionaries. For example, whitespace, regex, Chinese, Japanese, Korean, ICU. Specialized token filters for efficient indexing and indexing of numeric values and dates to support trie-based numerical range searching, language-specific streaming and stop word removal, creation of character or word level n-grams, tagging, UIM, etc. Using these existing building blocks or custom ones, it's possible to express very complex text analysis pipelines. With regarding finite state automata, the Lucene 4.0 here they requires significantly less main memory than previous releases. In the in-memory portion of the inverted index is implemented with the new finite state transducer. FST package. Lucene's FST package supports linear time construction of the minimal automation, FST compression, reverse lookups, and weighted automata. Additionally, API supports pluggable output algebras. synonym processing, Japanese text analysis, spell correction, auto suggest, and are now all based on the Lucene's Automata package, with additional improvements planned for future releases. This is regarding Lucene 4.0. Indexing. Lucene uses well-known inverted index representation with additional functionality for keeping adjacent non-inverted data on a per document basis. Both in-flight and persistent data uses variety of encoding schemas that affect the size of the index data and the cost of the data compression. Lucene uses pluggable mechanism for data coding and for actual storage of index data directory API. Incremental updates are supported and stored in index extents referred as segments that are periodically merged into later segments to minimize the total number of index parts. Document model. Documents are modeled in Lucene as a flat ordered list of fields with content. Fields have name and content data, float weight used later for scoring, and other attributes depending on their type, and with together determines how the content is processed and represented in the index. There can be multiple fields with the same name in a document, in which case they will be processed sequentially. Documents are not required to have a unique identifier, though they often carry a field with this role for application level unique key lookup. In the process of indexing, documents are assigned internal integer identifiers. Field types. There are two broad categories of fields in Lucene documents. Those that carry content to be inverted, index fields, and those with content to be stored as stored fields. Fields may belongs to either both categories. For example, with content both to be stored and inverted, both index and stored fields can be submitted for storing and or indexing, but only stored field can be retrieved. The inverted data can be accessed and reversed using a specialized API. Index fields can be provided in plain text, in which case it will be first passed through index analysis pipeline. Or in its final form of sequence of token with attributes, so-called token string. Token streams are then inverted and added to the in-memory segments, which are periodically flushed and merged. Depending on the field options, various token attributes such as position, starting or ending offsets, and preposition payloads are also stored with the inverted data. It is possible, for example, to omit positional information while still storing the in-document term frequencies on a per field basis. A variant of index field is a field where the criterion and storage of term frequency vectors are requested. In this case, the token stream is used also for building a small inverted index consisting of data from the current field only, and this inverted data is then stored on a per document and per field basis. Term frequency vectors are periodically useful when performing document highlighting, relevance feedback, or when generating search result snippets, region of text that best matches the frequency terms. Stored fields are typically used for storing auxiliary per document data that is not searchable but would be cumbersome to obtain otherwise. For example, it would require retrieval from separate system. This data is stored as byte arrays but can be manipulated through a more convenient API that persists it as UTF-8 strings, numbers, arrays, etc. Or optionally it can be stored using strongly typed API, so-called doc values, that can use more optimized storage format. This kind of strongly typed storage is used, for example, to store per document and per field weights. So-called norms, as they typically correspond to field length normalization factor that affect scoring. Index chain, the resulting token stream is finally possessed by the indexing chain, and the supported attributes, term values, position, offset, and payload data added to the representing position list for each term. The term values don't have to be UTF-8 string as in previous versions before Lucene 4.0. Fully support the Lucene 4.0 fully supports arbitrary byte array values as terms and can use custom comparators to define the sorting order of such terms. Also, at this stage, documents are assigned their internal document identifiers, which are small sequential integers for efficient delta compression. These identifiers are epimental. They are used for identifying document data within a particular segment, so that naturally change after two or more segments merged during index compaction. Incremental incremental index updates. Indexes are updated incrementally online simultaneously with searching by adding new document and or deleting existing ones. Subdocument updates are work in progress. Index extents are common way to implement incremental index updates that don't require modifying the existing parts of the index. When new documents are submitted for indexing, their fields undergo the process described in the before. The resulting inverted and uninverted data is accumulated in new in-memory index extent called segments. Using compact in-memory representation, a variant of codec, periodically these in-memory segments are flushed to the persistent storage using codec and directory abstraction. Whenever they reach a configurable threshold, for example, total number of documents or the size in bytes of the segments, the index writer class. The index writer is a high-level class responsible for processing index updates, addition and deletion, recording them in new segments, and creating new commit points, and occasionally triggering index comparison, segment merging. It uses a pool of document writers that create a new in-memory segments. As new documents are being added and in-memory segments are being flushed to the storage, periodically an index compaction merging and is executed in the background that reduces the total number of segments that compare the whole index. Document deletions are expressed as queries that select using Boolean match the documents to be deleted. Deletions are also accumulated applied to the in-memory segments before flushing and while they are still mutable and also recorded in a commit point so that they can be resolved when reading the already flushed immutable segments. Each flush operation for index compaction creates a new commit point recorded in a global index structure using two-phase commit. The commit point is a list of segments and deletions comprising the whole index at the point in time when the commit operation was successfully completed. Segments data that is being flushed from in-memory segment is encoded using the configured codec implementation. In Lucene 3.x, and earlier some segment data was mutable. For example, the parts containing deletions or field normalization weights, which negatively affected the concurrency of writes and reads. To apply the modification, the index had to be locked and it was not possible to open the index for reading until the update operation completed and lock was released. In Lucene 4.0, the segments are fully immutable. Write ones and any changes are expected either as a new segment or a new list of deletions, both of which the new commit points and the updated view of the latest version of the index become visible when commit point is recorded using two-phase commit. This enables to lock-free reading operations concurrently with updates and point in time travel by opening the index of reading using some existing past commit point. The index reader class the index reader provides high-level methods to retrieve stored fields. Term vectors and traverse the inverted index data. Behind the scenes, it uses the codec API to retrieve and decode index data. The index reader represents a view of an index at the specific point of time. Typically, a user obtains an index reader from either a commit point where all data has been written to disk, or directly from index writer. Near real-time snapshot that includes both the flushed and in-memory segments. As mentioned in the previously, segments are mutable, so deletions don't actually remove data from existing segment. Instead of delete operations are resolved when existing segments are open. So the deletions are represented as a bit set of live, not deleted documents. Global index statistics are not recalculated, so they are slightly wrong. They include the term statistics of postings that belongs to the deleted documents. For performance reasons, the data of deleted documents is actually removed only during segment merging. And then also global statistics are recalculated. Index reader API follows the composite pattern. An index reader representing a specific commit point is actually a list of sub-readers for each segment. Composed index readers of different points in time share underline subreaders with each other when possible. This allows for efficient representation of multiple point in time views. An extreme example of this is the Twitter search engine, where each search operation obtains a new index reader. Codec API, the Lucene 3.x used a few predefined data coding algorithms, a combination of delta and variable length byte coding. In Lucene 4.0, all parts of the Lucene code that dealt with the coding and compression of data have been separated and grouped into a codec API. This major redesign of Lucene architecture has opened up the library for many improvements, customizations, and for experimentation with recent advances in inverted index compression algorithms. The codec API allows more complete customization of how index data is encoded and written out of the underlying storage, the inverted and non-inverted parts, how it's decoded for reading, and how segments are merged. The 4D view of inverted index, the codex API represents the inverted index that data as a logical 4-dimensional table that can be traversed using enumerators. The dimensions are field, term, document, and position. That is an imaginary cursor that can be advanced along rows and columns of this table in each dimensions. And it supports both next item and seek to item operations, as well as retrieving row and cell data at the current position. For example, given a cursor at field F1 and term T1, the cursor can be advanced along this posting list to the data for the document D1, where the in-document frequency for this term TF can be retrieved, and then positional data can be iterated to retrieve consecutive position offsets and payload data at each position within this document. This level of abstraction is sufficient to not only support many types of query evaluation strategies, but to also clearly separate how the underlying data structures should be organized and encoded, and to encapsulate this concern in codec implementation. Lucene 4.0 codecs, the default codec implementation, aptly named Lucene 440, Lucene 4.0 uses a combination of well-known compression algorithm strategies selected to provide a good trade-off between index size and related cost of I/O sets and coding costs. Byte-aligned coding is performed for its decompression speed. For example, posting list data uses variable byte coding of delta values with multi-level skip list using natural ordering of document identifiers and interleaving of document IDs and position data. For frequency occurring very short list, according to the SIP's law, the codec switches you to using parsing strategy that inline posting with term dictionary. The term dictionary is encoded using a block tree schema that uses shared prefix deltas per block of terms, fixed line or variable size, and skip list. The non-inverted data is coded using various strategies. For example, pre-document strongly typed values for encoding using fixed length bit align compression similar to frame of reference coding, while the regular stored field data uses no compression at all. Applications may of course compress individual values before storing. Lucene 4.0 codex offers in practice good balance between high performance indexing and fast execution of queries, since the codec API offers a clear separation between frequency functionality of inverted index and the details of its data formats. It's very easy in Lucene 4.0 to customize these formats if the default codex is not sufficient. The Lucene community is already working on several modern codecs including P4 Delta, Simple 9, 16, 64, both likely to be included in the 64, and VS encoding, and experimenting with other representation for term dictionary, for example using finite state transducers. This is about 4.0. The codec API opens up many possibilities for runtime manipulation of posting during writing or reading, for example online pruning and sharding, adding bloom filters or fail fast lookups, for example, lookups, etc., and to accommodate specific limitation of the underlying storage, for example appending codecs that can work with append only file systems such as Hadoop DFS. Directory API. Finally, the physical I/O access is abstracted using directory API that offers a very simple simple file system like view of persistent storage. The Lucene directory is basically a flat list of files. Files are write ones and abstractions are provided for sequential and random access for writing and reading files. This abstraction is general enough and limited enough that implementation exists both using java.io.file NIO buffers in memory distributed file systems that, for example, Amazon S3 or Hadoop HDFS, NoSQL key value stores, and even traditional SQL databases. Now searching. Lucene's primary searching concerns can be broken down into few key areas which will be discussed now. Lucene's under topics Lucene's query model, query evaluations, scoring, and command search extension. We will begin by looking at how Lucene models queries. Query model and types. Lucene does not enforce a particular query language. Instead, it uses query objects to perform searches. Several queries are provided as building blocks to express complex queries. And developers can construct their own programmatically or via a query parser. Query types provided in Lucene 4.0 include term queries that evaluate a single term in a specific field, Boolean queries supporting and or not, where clauses can be any other query, proximity queries, strict pace, sloppy phrase that allows for up to n inverting terms, position based queries called spans in Lucene parlance that allows to express more complex rules for proximity and relative positions of terms, wildcard, fuzzy, and regular expression queries that uses automata for evaluating matching terms, disjunction max query that assigns scores based on the best match for a document across several fields, payload query that possesses per position payload data, etc. Lucene also supports the incorporation of fields values into scoring, named function queries. These queries can be used to add useful scoring factors like time and distance into scoring model. The large collection of predefined queries allows developers to express complex criteria for matching and scoring documents in a well-structured tree of query clauses. Typically, a search is passed by a query parser into a query tree, but this is not mandatory. Queries can be generated and combined programmatically. Lucene ships with the number of different query parsers out of the box. Some are based on Java CC grammars, while others are in XML base. Query evaluation. When the query is executed, each inverted index segment is processed sequentially for efficiency. It is not necessary to operate on a segment on a merged view of the posting lists. For each index segment, the query generates a scorer. Essentially an enumerator over the matching documents with an additional score index. Additional score method. Scorers typically score documents with the document at a time DAAT strategy, although the commonly used Boolean scorer sometimes uses TAAT, term at a time like strategy. When the number of terms is low, scorers that are leaf nodes in the query tree typically compute the score by passing raw index statistics such as term frequency to the similarity, which is significant, which is a configurable policy for term ranking. Scorers higher up in the tree usually operate on sub-scorers. For example, disjunction scorer might compute the sum of its children's scorers. Finally, the collector is responsible for actually consuming these scorers and doing something with the results. For example, populating a priority queue of the top 10 documents. Developers can also implement custom collectors for advanced use cases such as early termination of queries, faceting, and grouping of similarity results. Grouping of similar results. Similarity class implement a policy for scoring terms and query clauses. Taking into account term and global index statistics as well as specifics of a query, that is for example, distance between terms of a phrase, number of matching terms in a multi-term query, Levestein edit distance of fuzzy terms, etc. Lucene for now maintains several per segment statistics, for example, total term frequency, unique term count, total document frequency of all terms, etc. to support additional scoring models. As part of the indexing chain, this is This class is responsible for calculating field normalization factors, weights that usually depends on the field length and arbitrary user specified field boosts. However, the main role of this class is to specify the details of query scoring during query evaluation. As mentioned before, the Lucene 4 provides several similarity implementation that of well-known scoring models. TF, IDF with several different normalizations, BM25 information based, divergence from randomness and language modeling. Common search extensions. Keyword search is only a part of query extension. Keyword search is only a part of query execution for many modern search systems. Lucene provides extended query processing capabilities to support easier navigation of search results. The faceting module allows for browsing drill down capabilities, which is commonly in many e-commerce applications. Result grouping supports folding related documents, such as those appearing on the same website into a single combined result. Additional search modules provide support for nested documents, query expansion, and geopartial search. Here the addo update is connected to the document. Fields are in documents, and document is connected to the document writer documents writer via per field stored values, and documents is connected to text analysis chains, and document is connected to chains, and it is connected to document writer via per field token streams. And via text analysis chains. Delete is connected to document writer. Document writer indexing chain and segments are inside index writer. Document writers are connected to indexing chains. Indexing chains are connected to segments. Segment is connected to segments in codec via flush or commit. Here the segments can merge here, and the segments are inside codecs, and segments are connected to segment reader via open or reopen, and segment reader is connected to collection stats and term enum and doc and position enum. Collection stats and term enum and doc and position enums are connected to scoring API here. Segment reader and collection stats and terms enum and doc and position enums are in index reader. Index reader provides retrieve stored values here, and here the query search is connected to search is passed to a query parser. Query parse is connected to text analysis chains, and query parse is connected to query, maybe via sometimes via text analysis chains. Via text analysis chains. Query is connected to scoring API, and scoring API is connected to collector. Collector provides ranked results. Here the codex is connected to directory. There are files in the directory, and directory is connected to storage. Now this is the end of my presentation. Thank you very much for watching it.